Okay, good morning class. So this is already the last tutorial session this semester for this course. So in this worksheet, we are going to go through some of the questions related to the last topic you learned from the course, the two-sample test. So as before, I would like to spend a little time to give you an overview or summary of this formula. You can find all this formula from the lecture notes and lecture videos. Now for a two-sample problem, when we want to do a hypothesis test for two samples, that means we are comparing things from two populations. And usually, the main interest is to, a common scenario is to compare the population means. So we have the null hypothesis states that the two population means are equal. These two populations have the same mean. And of course, we need data, and there are different situations where we will need to use different formula and different test procedures, just like in one sample test or in constructing confidence intervals. So in case we have random samples drawn from the normal distribution, so you are told that, suppose you are told that the samples are drawn from normal distribution. And if the population variance are known, they are provided, then we will compute the test statistic using this formula. Actually, we are comparing the sample means because we want to compare the population means. And we divide by the standard error of the difference of these two sample means to construct this test statistic. In fact, this test statistic also takes this general form. So equivalently, the null hypothesis states that the two population means are the same. This is equivalent to saying that the difference in the population mean equal to 0. So actually we have an intrinsic null value in the null hypothesis, which is 0. And the test statistic will test this form. We start with estimating the difference in the population means, compare this to the null value, and divide by the standard error of the estimate of the difference in the sample mean. Okay? So in a lot of the test statistics you've seen before, in one sample case, we also have this kind of format. A point estimate minus a null value in the null hypothesis, divided by the standard error of the estimate, which is this form. And of course, the rejection region will depend on the alternative hypothesis, depending on whether you want to test on two sides or one side. So it takes similar form. We have the difference of the population mean comparing to the null value, whether we are interested in both sides or just one direction, to the right-hand side of the null value or the left-hand side of the null value. Then we have this rejection region. Okay? So the rejection region here is quite similar to the one sample case. And in case if you are not told that the population are normal distribution, the distribution is unknown. But when the sample size are large enough, we can still do some approximation and use the same method, same formula, same test procedure, same rejection region to do the test. And this is the case when the population variance are provided. Now, if the population variance are unknown, then of course we need to estimate them. And there are also two different cases, whether you assume them to be equal or not, just like in confidence intervals. So if you have unknown population variance, but you can assume that they are equal, then we will estimate them using a common or pooled sample standard deviation as P. Then we combine the two samples variance together and then compute the pooled sample variance, take the square root, we can obtain this as P. And then we substitute into this formula, we can compute the t-test statistic. And for the rejection region, they are similar to the previous situation, except that the quantiles, the normal quantiles, are replaced by the t quantile, obtained from the t distribution table. And the degrees of freedom is obtained as combining the degrees of freedom from the two samples. the sum of the sample sizes minus 2. Just like the contours, we used it for constructing confidence intervals. Now, in case when the population variance are known and you cannot assume them to be equal, they are not assumed to be equal, for different population variance, then we need to estimate them separately. We cannot pull them together to have a single and common estimate. Then the t-test statistic will test the form as the z-test statistic, which is this one. But the variance, the population variance are unknown, so they are replaced by the sample variances. And the rejection region will be also based on the t contours. But this time, the degree of freedom needs to be approximated by a complicated formula. Of course, if the sample sizes are large, when m and n are large, like larger than 30, then usually this A will become also large. And these t contours can be well approximated by the normal contours. So for large samples, even you don't know the population variance, we estimate them using the sample variance. If m and n are large, then we can also compute this test statistic and then use the normal contours to determine the rejection regions. Now finally, we also have this hypothesis that involves the population proportion. Comparing two population proportions to see whether they're equal or to see whether the difference of them equal to 0. So we also have a 0 as the null value. And this is the formula you'll find in the lecture notes and also the lecture videos, where x bar and y bar represents the sample proportions from each sample. M and n represents the sample size from each sample. So it also takes the form comparing the estimate of the difference with the null value and then divide by the standard error of the difference of the estimate. Okay? So the denominator here represents this standard error. But actually, just like in one sample problem, sometimes if you read some other textbook, you will find that another formula will be also used. I mention this just because you will find that although this was stated in the lecture notes and lecture video, this formula is actually used in the solution of this worksheet. So I also like to explain this a little bit. Now this is the formula. Under the null hypothesis, we assume them P, H, and Py are the same. So when if they're the same, then if null hypothesis is true, we have a common proportion. And then we can combine the two samples together to obtain a common estimate of this common proportion. So that's why we have this P bar, which is called the pooled sample proportion. This pooled sample proportion is just simply adding up the counts in each sample divided by the total sample size. So it is just like instead of dealing with two samples separately, we combine them together, treat it as a single sample, and then determine a single sample proportion, which is this P bar. So we use this P bar to evaluate this standard error in the denominator. So this is how this version of the test statistic is obtained. Now you may wonder which one we should use. Now both are acceptable. Both can be used. And in most of the situations, the conclusion will be quite consistent. Even you use this one or you use this one. But in the solution of this worksheet, this formula was used. So that's why I would like to tell you this additional formula. And the rejection region will be quite similar to the rejection region we have seen before. And the contour we use are the normal contours. So basically, this will be the two-sample test basic version of the two-sample test you've learned from the course and you may encounter probably in the final assessment. Is there any question? So here are a few questions in this worksheet, and they are all related to two-sample test and make use those formula and rejection regions. So see whether you'll be able to answer some of these questions. Probably we'll start with question number 3. Okay. Just spend a little time to work on this question. Okay, maybe I will just go through this question and show you a brief walkthrough. Now, the first step in doing this test is to identify the hypothesis to be tested. In some questions, the hypothesis will be explicitly stated, just like question number question number 1 in the worksheet. In the question number 1 in the worksheet, you'll see H0, H1, they are stated explicitly. But in this question, also in some other question, sometimes the hypothesis is not given. So you need to identify or formulate the hypothesis yourself. And it depends on the purpose or the objective of the test, which is based on this question. Test whether the data provides sufficient evidence to indicate a difference in mean. So what we are interested in is to see whether there is a difference, but not a particular direction. One greater than the other one smaller than the other one. We don't have this kind of objective stated in the question. It only claims that, or it only suggests that we want to test whether there's a difference. And therefore, we are going to do a two-side test. So this is how we identify the hypothesis. Now this is important because the alternate hypothesis will affect your rejection region and the conclusion. Now, the next step is to identify the test statistic to be used. So in this case, we are told that the distribution are normal, but we are not given the population variance. But we are asked to do this under two different assumptions, whether they are not equal, under the scenario when they are not equal, and another scenario when they are assumed to be equal. So we do it step by step, starting with the assumption that we don't have the assumption that they're equal. So for unequal population variance, the test statistic, when the population variables are unknown, we use this t-test statistic. Comparing these two sample means, divide by their standard error, which is determined using the sample variances. So this is the test statistic we are going to use. The test statistic, the bottom line is that you must be able to compare it using the sample data. And you need to also determine the rejection region. Under what scenario, under what situation, or what value of this t, we will reject the null hypothesis. So we need to compare the absolute value of the test statistic with the quantile. The reason is that we are doing a two-sided test. When you are doing a two-sided test, then we will take the magnitude. And compare with the quantile. Now, it depends. For this case, when the population variance are unknown, we replace them by the sample variance, then theoretically we should use the t quantile. And they are not equal, so the t quantile will have a degree of freedom computed using the complicated formula, which is this one. Actually, it falls under this scenario. We need to compute the degree of freedom and then compute the quantile using this formula. But it is kind of too complicated, and we see that in this question, the sample size are larger than 30. So these samples can be regarded as large samples. And therefore, we can simply approximate the t quantile by using the normal quantile. And we need to allocate half alpha to both ends to compute this quantile, just because we are doing a two-sided test. So for alpha equal to 0.05, this normal quantile is equal to 1.96. So we have the test statistic, we have the rejection region, the rest will be just routine computation. The test statistic is computed by putting everything we know about the sample in the test statistic. Difference in the sample means divided by the standard error, which is square root of the sum. This sample variance divided by sample size. and add them up together. And it gives a value equal to minus 2.49. And since we are doing the two-sided test, so we will just simply use the magnitude. So we drop the negative sign. Compare this magnitude of the test statistic with the critical value. We find that it is greater than the critical value. So the conclusion of the test is that we reject the null hypothesis at 5% significance level. The data shows enough evidence for us to indicate that the two population means are different. So this is how, in general and typically, we do the two-sample t-test. Any question? Now, the second part is similar, but this time we assume them to be equal. The two population variants are equal. Then the test statistic is computed also comparing the two sample means in the numerator. But for the denominator, the standard error will be computed using a pooled sample standard deviation. When the population variants are assumed to be equal, then in the denominator, in the standard error, we use the version that is based on a pooled sample standard deviation. And we also compare the magnitude of the test statistic with the quantile. Now this time, you may either try to use the t-quantile, because this time the degree of freedom can be easily computed without doing that complicated calculation. N plus n minus 2 is equal to the sum of the sample sizes minus 2, which is equal to 70 minus 2, 68. Now this quantity cannot be directly obtained from the table. You may obtain it from using the R, okay? Using the R QT function, you can easily compute this quantile. Or you may also consider using the normal quantile as an approximation. The values not deviate a lot. So I don't have enough space. Maybe I add one more page. So we compute the test statistic starting with the pooled sample variance, or the pooled sample standard deviation, which is the square root of the sample size minus 1 multiplied to the square of the sample variance, and do it for the other sample, add them up together, divided by the sum of these two degree of freedom. And we substitute everything into it. I don't have a calculator here. I just copy this from the solution. So take the square root, because this is the number within the square root sign. So this 17.7 is the pooled sample variance. We take the square root of it, we get the sample standard deviation, the pooled sample standard deviation. So the test statistic will be computed by comparing the sample means divided by this pooled sample standard deviation multiplied to the sum of the reciprocal of the sample sizes, and then take the square root. And it is equal to minus 2.48. So the absolute value, the magnitude, is also greater than the critical value. No matter whether you use the exact t quantile or you use the approximated normal quantile, you also get the same conclusion. So we draw the same conclusion. The null hypothesis is rejected. So in fact, in this case, whether you assume the population variance are equal or not, you will find that the test statistics are quite close to each other. The test statistic computed before is 2.49, and here it is 2.48. Okay. That's because the two sample variances actually are quite close in values. Is there any question? Now, we can move on to question number 5, which is another kind of test involving population proportions. So the first step also try to identify the null hypothesis and the alternate hypothesis. Okay. So try to spend a little time to work on this question, and let me know if you have any problem. Somewhere between 1.99 and 2.0. Right? Because it is between 60 and 80. 6 is between 60 and 80. So therefore, the quantile will be somewhere between 1.99 and 2.0. So you can still make use of these two numbers for doing comparison. Right? Because this is greater than 2, and of course it must be greater than the quantile.
So the test will just
yeah.
Gas between the two.
Yeah, you can just, because that provides a range of the quantile. You don't need the exact value as long as you can draw the conclusion.
Yes.
So I have a few minutes left, so I would like to explain to you the key ideas to work on this question. So this is a question that is related to the comparison of population proportions, proportion of people who believe in extraterrestrial, comparing two populations who have attended college and those who have not attended. Now, according to the description of the data collection, we have a random sample of N1 equal to 100 people obtained from those who did not attend college. So those who did not attend college is the first sample. Those who had attended college, they form the second sample. So this is the notation, the index. So we denote P2 as the population proportion corresponding to those who have attended college. And P1 indicates the proportion among those who have not attended college. Now, to formulate the hypothesis, because it is not explicitly stated, the null hypothesis may state that they are the same. This is the hypothesis you have seen throughout the whole course. But now, what is the alternate hypothesis? It depends on our interest. What we are going to test. It is suggested by this sentence. Do these results indicate that the proportion of people among those who have attended college is higher among those who have attended college than those who have not? So we have a particular interested direction in the comparison. We are going to see whether P2 is actually higher than P1. And therefore, the alternate hypothesis should be based on this interested direction of comparison. Okay? So we have a particular interest, direction of interest in doing the comparison. We want to see whether P1 is actually smaller than P2. So we put it in the alternate hypothesis. So this is how we formulate the hypothesis or to identify the hypothesis to be tested. Now, this is important, as I mentioned before. This affects the rejection region, how we draw the conclusion from the test statistic. Now next, we need to determine the test statistic. Now for two sample proportion problem, the test statistic will be this Z statistics. Comparing the sample proportion. So H1 bar, H2 bar represents the sample proportions from each sample. Divided by the standard error. Now there are, as I mentioned before, there are two formulas. Either you use these two sample proportions separately, adding up two terms, or we combine them together to use the pooled sample proportion. So to be consistent with the solution, here we use the pooled sample proportion. So this is the formula if we use the pooled sample proportion to formulate the test statistic. And we will reject the null hypothesis if the test statistic is found to be too small. So the rejection region should be consistent with the alternate hypothesis. The alternate hypothesis is saying that P1 is less than P2. So under what scenario P1, that will indicate P1 less than P2, that is when this is smaller than this. That is when Z is smaller. That is when this test statistic is smaller than the quantile from the normal distribution. Now this time, since we are doing a one-sided test, so we don't need to allocate alpha to both sides of the distribution. So we don't need to divide alpha by 2. For 5% significance level, this is 0.95. So we reject the null hypothesis if Z is smaller than minus 1.645. Now notice that this time we are not using the magnitude of Z because we are not doing a two-sided test. So the rest will be routine calculation. The first step is to find the sample proportion from the first sample. The count is 37 divided by 100. So for the first sample, the sample proportion is 0.37. For the second sample, It is 47 divided by 100. 0.47. And then we compute the pooled sample proportion. It is just like we pool the two samples together, combine the counts, combine the sample size, and then we take the ratio. So the pooled sample proportion is 0.42. So we substitute everything into the test statistic. It is computed as minus 1.433. Now, we need to compare with the critical value. And it is actually greater than the critical value. The critical value is minus 1.645. We are not going to take the magnitude. So this is greater than this. So it didn't fall into the rejection region. Rejection region is those test statistics smaller than this. And therefore, we draw the conclusion that the null hypothesis is not rejected. At 5% significance level. So we don't have enough evidence to claim that P2 is greater than P1. Okay? So this is also a typical kind of question in doing two sample tests in terms of the proportions. Now, if you're interested, you may just try to use another formula, which is this one. This one, this formula shown in the lecture notes or lecture video. You do the calculation again using this formula, you will find that the test statistic computed actually will be quite close to what we computed before. And you will draw the same conclusion. Most of the time, the conclusion will be quite consistent using either formula. Now, so this is the end of this session, and also the end of this all these tutorials in this semester. So there are some more questions. You may try to work on them, and you can find the solution from Blackboard. In case if you do the revision, working on this worksheet, or you do some past paper, you encounter any problem, just feel free to let me know. You can send me an email, or if you want to have a face-to-face discussion with me, it's all welcome. You can make an appointment with me. I will be around during the break. Okay? So thank you for attending my class, and good luck to your final assessment.
Question we just talked about, we did not use the A, right? Because
we just approximate by using the norm, because it is large, the sample size is large. So in case when the sample size is small and you really need to use this, then you need to compute the A using the formula.
So normally if the sample is large, then we don't.
We just simply use that. And you will find that if the sample size are not large and you have to use this formula to compute the A, then you will find that A is not an integer. But normally the computed A will not be an integer. So you can also just simply make use of the technique I taught you before.
Yes.
Either you use the computer, of course, or you use the table So for example, if the A computed is equal to 5.6,
Yes.
then you can use the t values for the default freedom equal to 5 and equal to 6, you have two quantities. And then you have the range.
And also for our coursework, so in the question I tried and use the n-1, but for the previous year's coursework, and sometimes it does not use the n-1. So
there are two formulas for the sample variance.
oh,
One is divided by n-1, one is divided by n. Okay, but in this course, all the sample variance computed are based on the formula divided by n-1.
okay.
So the formula divided by n is called the MLE. That is the MLE. And divided by n-1 is an adjustment to adjust it correct into unbiased.
Correct into unbiased.
Yeah.
Okay. All right. Thank you.